Welcome everyone. This is the EasyPower webinar series. My name is Jim Chastain. I'm your host for today. And we're very fortunate to have with us an esteemed gentleman who has a very exceedingly nice resume in the field of arc flash. Dr. Lee received his bachelor and a master's degree in electrical engineering from National Taiwan University in Taipei, Taiwan in 1978 and 1980 respectively. In 1985, he received a PhD from the University of Texas at Arlington in electrical engineering. Also in 1985, he joined the University of Texas at Arlington, where he's currently a professor of electrical engineering department and director of the Energy Systems Research Center. Over the course of more than 10 years, beginning in the year 2004, a multi-million-dollar research project sponsored by IEEE and the NFPA involved a series of over 1,800 arc flash tests performed in high-voltage laboratories, and it was Dr. Lee who led this research project, which evolved into the IEEE 1584 model. We are fortunate to welcome to our podium Dr. Wei-Jin Lee.
Good morning, good afternoon, or good day, everybody. And I'm very happy to share with you on the IEEE STD 1584 2018, the guide for perform arc flash hazard calculation. And then I try to basically give some background information, because I know since that this webinar is hosted by Bentley, and I believe everybody understands how to run the arc flash calculation. So on that part, I will skip that part and try to give you some behind the scene, the activity, and then so hopefully that give you a better idea, better understanding on how the model was developed. And as we know that electrical incident represent a relatively small percentage of the work-related incident. However, they are disproportionately fatal, and in the case of the burns, may result in extended hospitalization and rehabilitations. So, if you, according to Richter, electrical related fatality is the number 5 leading cause of death in the workplace. And when you look at the arc flash from the arc flash point of view, that IEEE 1584 and the NFPA 70E have been developed to protect the safety of the workers. And from the approach point of view, NFPA 70E try to use a tabulized one. However, from the IEEE 1584 point of view, since we are engineers, so a lot of time we try to do a more quantitative result and give you the formula to do the calculation or the estimations. So when you talk about arc flash in the regular setup in the electrical installation, you all have enough insulation level, so it will not create any leakage current or any path between two conductors. And however, in some case, sometimes we call it a screwdriver alert, and somebody during the work, and then they drop the tool, they create some short circuit. So once the short circuit happens, then that bounce into that, it's going to create a lot of heat, and the heat will then ionize the air. So on that way, that will basically create the breakdown of the air. So the arc flash is basically from this way here. Once the ionized air, then even the tool bounce away, then the current continues. And for this one here, it will be a sudden release of the heat. And basically a lot of time, if you have ever experienced, I hope it doesn't, it's going to create a big bump, and it's so sudden release of the energy. And on that one, that can basically, cause an injury or even create a fatal of the worker even nearby. And of course, on this one here, when you talk about the arc flash, if it is a short circuit, then since R equal to 0, so there's no energy release. So from the arc point of view, there's a resistance between the two conductors. So that I square R produce the energy that can basically release millions of joules in one incident. And for this one here, this is basically, I know most of you have seen this basically this video clip, and it's from the YouTube. And then you can see in one moment everything seems normal, and however all of a sudden that basically on this one here is more like they are wrecking the circuit breaker and the misalignment on the circuit breaker that caused the short circuit and then caused the arc flash. And so the first edition of the 1584 was published in 2002. So at that time, that we only have two models. Okay, one is basically you can see here. This is an electro over there. This is a vertical electro, and inside the box. And these are the calorimeter that basically try to measure the incident energy. And the other configuration is the vertical electro in the air, in the open air. So on that calculation point of view, that is a very relatively simple configuration. Everybody can, when you look at in the field, and when you look at the setup, you can identify what kinds of configurations. So at that time, it's basically we only identify or provide the formula for two configurations. And right after the publication, people basically criticize, say, okay, well, this did not represent the whole configuration. So in 2004, as Jim mentioned, okay, in 2004 they formed a committee between the NFPA and the IEEE. They say, okay, well, let's put two organizations together and then try to develop basically the model that can be used for both organizations. And for this one here, with about 10 years effort, I was invited into basically the collaborative research project. We call it the IEEE NFPA Arc Flash Phenomena Collaborative Research Project in 2008. And after 10 years effort, in 2018, the 1584 was published. So that is basically in the 1584, because it was a little bit rush, and then so in 2002 the model is based on about 300 tests. For the 1584 2018, I have run more than 2,000 tests, but some of the tests that we say, okay, it doesn't sustain. It did not sustain. So the useful information is about 1850 tests. And 1584 only provide two configuration, but for the 2002 model only provided two configuration, and the 2018 we extended to 5 configurations. So on this one here, when you look at this one here, okay, this guide we provide the model into an analytical process to enable calculation of the predicted thermal instant energy, arc flash boundary, and the arcing current. For this one here, okay, so every model has a limitation. So on this one here, we basically cover the 208 to 15 kV, and it's a 3-phase AC current, AC system. So on this one, the purpose of this guide is try to have a qualified person to analyze the power system for the purpose of calculating the IE, and that is basically that employee could expect during the operating or maintenance work if something happened. Okay, so that is basically that also provides some information for the owner to basically help providing appropriate protection. And for this one here, as I have mentioned, this is only for three-phase. So it doesn't cover the single-phase AC system. And then we basically just provide it because, okay, well, you can extract it from the three-phase. And then in the 1584 2018, they also provide some guidance for possible application on the single-phase. And it doesn't go with the DC either. Okay. So it doesn't cover the personal protection equipment, the PPE side, because sometimes when you try to determine the PPE, in addition to the arc flush, you have some other considerations. So it's basically the recommendation for the PPE is not in this one here. And then the other one is the one big difference between 2002 and the 2018. Is in the 2002, they say, okay, well, if the 240 volt below and the 125 kVA the transformer, then that arc is unlikely to sustain. However, when I did a separate test to try to identify this issue, then we see in some case that we did see the sustainable arc during the test. So I run more than 100 tests in one of the lab, and then so this one here is actually at the time that when I run it, we just go down to about 2500 amps. And then in the working group, they feel, okay, well, from the safe side, more conservative side, they put the 2000 amps. So they say, okay, well, it's it's possible, but less likely in the three-phase system, operate 240 volt, nominal or less, and variable short circuit current or 2000 amps. And when they put the 240 volt over there, it's basically from, if you think about it, it's basically on the high side of the 208 120, and also all the single phase, basically, okay, the three phase, the 120 208 system, and then you plus the 5% over there. So if you look at the range over there, this is the 2018, it pretty much match the 2002, the range, okay, from 0.5 to 106 amps for voltage below 600 volt. And then from the 600 volt to 15 kV, it's 0.2 to 65 kA. So for this one here, the big difference between the 2018 and the 2002 is that if you pay attention on the 2002 model, on the 1000 minus and 1000 plus, you are using a two formula, and they have a discontinuity result. Okay, they come out with a different result. For this one here, it's basically, okay, well, there's no gap between the calculation, even though we look at it as the 600 volt on the basically on both sides. So, but the result is continuous. And then of course, since this is for the low voltage, to have a sustainable arc, then the gap will be a little bit smaller. Okay, so when I run the test, I will basically follow the UL standard, AA9 standard, and then for the high voltage, we use the BIL as a reference. And in the 2002 model, it doesn't consider the enclosure size, and for the 2018, we do consider in enclosure size. Here we put it on 49, and actually you basically run into the 49 and 50. They are about the same. And then also you have a 5 configuration. We call it the VCB. It's a vertical electrode in the cubic box. Okay, and then we at that time during the test we use the cubic box, so we basically just name it as the cubic box. It's a metal enclosure, and then VCBB is the vertical electrode in the metal enclosure and with barrier. HCB is the horizontal inside the metal enclosure, and then VOA is the vertical open air. HOA is the horizontal open air. So on this one here, you can see here when you look at it, okay, the basically for this configuration, and this is the vertical one, and if I okay, so if I put in this one here, you can see, okay, the plasma is basically go downward, and so this is one of the configuration in the 2002. Then if you come into here, it's a this is a horizontal configuration. So if you look at this one here, we basically assume this is the worker standing at here, and then you can see the difference between the vertical and the horizontal. Horizontal, the trajectory of plasma basically fly toward to the worker directly, and this is much serious situation. Okay, so this is the basically we tried to, for this version of development, we try to basically look at it. Okay, what is the configuration, and normally you're going to see much severe situation like this one, and during your calculation you will realize, okay, from the vertical, the basically vertical configuration and horizontal configuration. Horizontal configuration, the protection boundary, it's a little bit shorter than the vertical configuration. This is because when the plasma flow over there, okay, and then hot air is going to go up quicker. So when you move the measurement point further away, then the thermal, the degradation, that basically the drop because of hot air blow up, and then so it doesn't touch the sensor. So on that way, from the calculation point of view, that horizontal configuration, even those at the shorter distance, they have a higher instant energy. However, their protection boundary will be shorter, with shorter distance. And for this one here, this is the VCBB configuration over there, and you can see, okay, well, it's this is the 4.16 kV, and with 63 kA. And one thing that I have to mention is, okay, if you look at it, there you are going to see a metal droplet here, and from the measurement point of view, metal droplet, we won't be able to measure the major droplet. It's a hot spot. So this is another thing that you have to consider. And of course, when you try to look at the arc fraction study procedure, everybody know that. Okay, I'm basically you understand the configuration and obtain the parameter, calculate your circuit current. Okay, and then estimate the arcing current. From the arcing current, you estimate the arcing duration, and of course, when you use the EasyPower, they basically help you do all this because they have a table of the fuse curve or a relay curve, so you can estimate the arc duration, and then you try to determine the working distance. Normally, is arc initiation point to the worker's chest area, the distance. Then we consider that one is the working distance, and then you try to estimate the instant energy, and then you try to calculate protection boundary, and then of course the protection boundary you will base on the 1.2 cal per centimeter square. That is from the Stoll curve. So for the difference between the 2002 and the 2018 on the 1584 is we have 3 additional configuration. So on that way, the people always ask, okay, how can I determine which configuration to use? Okay, so here I give an example here. It's basically from the basic physics. We call it the right-hand rule. So you can see here, this is the F, this is the B, is the flux, and the I is the current direction. So here is your current here. And the B is basically created by this one. The current flow inside the conductor is going to create. So based on your right-hand rule, you can see, okay, the B flux direction here, and then the interaction with this one. So the F coming to here. So you when I show you the vertical configuration over there, the plasma trajectory is go downward. This is basically you are using the right-hand rule. And for this one here, this is on MCC, and we basically initiate the fault at this point. When you initiate the fault at this point, this is more on the VCB or VOA, depends on the enclosure size. And you can see here that the trajectory is going downward. For the same equipment, if I have a fault, if I basically initiate arcing fault at this point, which is at this point here, then it becomes a horizontal. So you can see here that basically coming to the horizontal. Okay, so when you try to determine the configuration, then you try to first thing you have to do is determine at what point you think the arc flash will happen. Okay, and then that determine the trajectory of the plasma, and then you determine the configuration over there. So here is basically you can see, okay, this is the black mark over there that basically show you how the arc flash, the trajectory, the plasma trajectory that flow during the incident. And so on this one here, as I have mentioned, I'm going to give you some background information. Okay, so this is the measurement equipment on the arc flash test. And so the first one is the basic, of course, you have to collect the data. So the data acquisition system and the thermal measurement system. So at the beginning that we used the off-shell product, and then it's basically USB connection. So it basically, according to the spec, was pretty good. The sampling rate is more than 200K, and then they give you an 8 analog channel. Well, unfortunately, on this one here, it did not have enough isolation. So also this one, it will be inside the lab, and then you don't want to stay in the lab. So we basically use a USB extender, and then use the USB to the Cat5. So we will be able to measure the basically collected data 300 feet away. And yeah, it was basically work for the 480 volt testing, and unfortunately, it was destroyed. That in the higher voltage test, because you can see here, okay, on the measurement side, that here you are using the calorimeter over here, and the calorimeter is the thermocouple, and the front end is a copper. So the plasma basically touch the surface of the calorimeter, and then that touch the high voltage. So insulation becomes a very important one. And also the thermocouple output is on the millivolt. This one here, okay, 480 volt, that's the minimum. The 208 is the minimum. Then as high it can go to the 15 kV. So on this way here, since some small difference, it's going to go back and then destroy the circuit by itself. So this, yep, during the test, the second test, it was out. So I went back and then come back and come up my own design. Okay, so on this way here, this is the basically okay the calorimeter here, and then you have a thermocouple go through a conditioner. So that basically converting to the voltage, and then go through the isolation here, and then get into the compact reel, and then use the optical connection, okay, fiber connection, that basically between the unit and the computer. So on that way, we will be able to create isolation, and then so that is the basically okay. Well, for the sake of the equipment and for the sake of the person. And so for this one here, the slot calorimeter is based on the STM 1959. So this is the 4 centimeter, and with the 1.3 minute, the basically okay that the depth of the copper is the basically 1.6 millimeter thick, and then it's 18 gram. So then you drill a hole in the middle, and you put the thermocouple over there, and the behind of it is this is the insulator, and it's the air chamber over there. Okay, so on this way here, that temperature rise, that translate if you do it at 18 gram over there. So if you 1 degree temperature rise equal to 0.135 calorie. Okay, so that is the basically has a direct translation, and then we can measure the temperature rise and then get into the instant energy. So on this way here, you can see here the surface is a flat black, and during the test we did some experiment with a different with the painted with a silver tone, and then try to see okay how much difference will be. And also, since it's difficult to predict, we can somewhat predict the trajectory of the plasma. So, but we try to basically make sure we cover all the range. So every test we put in 7 calorimeter over there, and then with the matrix over there, so we will be able to find, because when you try to do the calculation, we basically look at the highest temperature rise, because the damage is not based on the average temperature rise. The damage is based on the most severe temperature rise part. Then the other one is the sound. Okay, so yes, if you look at it, okay, that is different weighted sound that for the people, and then that is basically on this way here in our testing, we use the A weighted applied to the instrument major sound level in the effort to account for the relative loudness. And you know the OSHA have a requirement that basically for the 140 dB you need hearing protection. Okay, and so the sound measurement, that basically we use the microphone, and then that basically use all the microphone comply with the NCS 1.4, and the whole event is less than 200 milliseconds. So weighted C peak is recorded, and then so the sound level affected by, because when you do the experiment, the sound level are affected by the size and the shape of the test lab, the magnitude of the short circuit current. So that is basically the correlation between the sound level and the arc duration is very small, because the louder boom it's basically at the beginning. So normally it's just happen at the beginning. So the arc duration that doesn't really change that much. Okay, and so we basically try to look at it, okay, on the first time waiting or slow time waiting, and the impulse time waiting, based on the specification. Then this is the basic. This is the microphone over there, and this is the sum of the test result. Okay, it's a 3 meter away, and you can see here, all this basically every test is more than 140 dB. So on this way here, this is a 2700 volt, and since that basically we don't have enough information, and then we run the test at different lab, so that basically the basic conclusion is a hearing aid should be included as part of the PPE, because you see it's always more than 140 dB. And then the pressure measurement. The pressure measurement, okay, well, if you look at some of the report or some of the information on the website, and then they will tell you this is basically, okay, it's 21, that I remember the number is 2100 psi. It's a pound per square inch, 2100 pound per square inch. That is a lot, okay? Because if you look at your chest area, you have about, okay, well, probably 100 square inch. And then you basically have a 1 ton of the force applied to, well, more than 1 ton. It's a 2100, basically 2100 psi, then times 100 square. So it's almost 100 ton. And then if this is the correct number, then the worker will be squeezed to death. So this not the basically. Then we try to look at it, how to, and of course in some case the worker get knocked off the ladder, and then we try to see, okay, well, what kinds of pressure that really happened during the incident. And so at the beginning, I thought it was an easy one, just to put the pressure sensor over there. So this is the pressure sensor we use, and it's a piezoelectric sensors. And of course, a lot of sensor, they use it's a diaphragm inside, and when they use the diaphragm inside, that basically they are heat sensitive. So we don't want during the test, the first test, we destroy one sensor. Okay, this sensor is about $900. So we say, okay, well, then let's put it in the site, and put it in the site, and then you measure a negative pressure. Okay, because the balloon effect, then you have an airflow flow through, and then you basically get the negative measurement. So it doesn't work. Then, so I come out with the idea, say, okay, well, let's use a pendulum here. You can see here, I have a pendulum here, and I know during the arc it's going to have a lot of smoke, so I tie a knot here, and this is the metal plate. So when you have a metal plate over there, they push it over, so you can see here, and then during the arc, then you see, okay, here you can see how they move. Okay. So this one that move over, and so on that way I know how far the pendulum move, and then what is the speed, and then we can basically come here and calculate what is the pressure. And on this particular case, we have about 0.6 to 0.8 psi. And the other one that we have used is to basically use during the arc flash. I have a high-speed video over there. So based on the 2 consecutive frames, I will be able to look at what is the airflow speed. And then from the airflow speed, I will be able to estimate the pressure. And but for this one here, because you need the open field here, so it doesn't obstruct the airflow. And arc flash test is relatively expensive. So it's basically, okay, normally you are talking about $1,500 to $2,000 per test. So we basically say, okay, well, yes, it works, but it's not the really economic solution. We have a limited budget. So then I come up another one, use the LVDT, the linear voltage differential transducer. So this is basically based on the transducer, the movement of the transducer here. They have a 2 coil, and this is basically the move. And then try to look at it on this way here. We will be able to look at how fast they move, the speed, and also the distance. So this is basically the very simple Hooke's law, and then we can change the size of the plate. So on that way, we can basically adjust the sensitivity. And here is this is the metal one. So here, this is the insulator here. So it will they are not going to have any induced current get into the transducer. So for this one here, come up, it's basically you are talking about the 0.715 psi, and then it's about 103 pounds per square feet. So this is basically from the distance. And well, unfortunately, we designed the test equipment. However, we did not have enough test results. So I did not create a model for the pressure. And the other one is the light intensity measurement. Okay, so yes, according to the OSHA, about the eye injury account for about 4.2% of all arc flash related injury. And then some people experience a temporary blindness due to the sudden bright light. And then also the high intensity light in the visible infrared and the ultraviolet light can damage the important structure such as the cornea or the retina of the human eyes. So, but on this way here, you can use eyeglasses that block the IR and UV, and block the visible light, because the worker rely on the visible light to do the work. So then we try to look at it. Okay, well, from the visible light point of view, it's about 380 nanometer to 760 nanometers, and that's the human eye. So then, also the human eye they have a different sensitivity to the different wavelengths, and also for this one here, this is basically during the lighted area. So this is your eye sensitivity. This is the green one is the sensitivity of your eye, the typical human eye under the dark area, dark environment, and this is the relatively the illuminated environment. And normally the workspace, you have certain light level over there. So we are following this curve. And for this curve, we are fortunate to have to find an IC, for the integrated circuit that they designed it that follows the human eye. However, this one only can work on up to 100,000 luminance. So we have to look at it. On the 100,000 luminance over there, then the arc flash is much higher. So we basically use a neutral density filter, and then I'm using the socket, 1.25 inch socket as a protection. So on that way, and then also have a separate current. So this is a surface mount device, and that come out a pretty good design. And basically, we basically put it into the three measurement point, and with the 3 meter, 4.5 meter, and the 6 meters. So then you try to aim it in the same direction, same point over there. So, but when you have a three you try to use an eye to try to align it. Sometimes you create some misalignment. You can see here the response is a little bit different over there. Okay, this is because of the misalignment, because they have every chip has a line of sight. So to solve the problem, I basically create a very relatively easy solution. Use a laser pointer, and then try to align it, and then this basically, okay, it's a $1 solution. So that basically solved the problem. And for this one here, this is the basically recorded light. And on this one here, this is the blue one is a 6 meter, and for the red one is the 4.5 meter, and then the green one is the 3 meter. So, and then with this one here is the basically, okay, with the different configuration, different current level. Okay, so for this one here is the 10 kA. Okay, and then this is a 12 cycle, and that 2700 volts. Okay, it's basically 4.5 inch over there, and so you can see here that basically, okay, that give you the measurement, and we have more than 1500 measurement over there. So yes, there's a paper we have published that describe how to derive the formula for the light intensity measurement estimation. Okay, and so on this one here, that I have to basically give the credit to the sponsor. We have a platinum sponsor, and we have a gold sponsor, silver sponsor, and the total budget for this project is about $3.7 million cash and in kind. And so that is the basic. Without their support, that it's impossible to have this project complete. And that basically one thing that we have to. I'm sorry that I have to close the door. Yeah, one thing that I always try to emphasize is, okay, so this is the calorimeter, and that this is the measurement point. On the side is insulator. So you can see a lot of copper deposit on the insulator side, and this part, it's basically you're going to see a hot spot over there, and it's difficult to do the measurement. The other one is, okay, this is the lens. You see on the light measurement, okay, I'm using a neutral density filter, and this is 10 feet away. So nobody want a copper droplet on their eye. So the eye protection is very important. So this is, I always tell people, you only have one pair, no spare. So that eye protection is very important. So with that, I would basically stop it here, and then I'll ready for your question.
That was fascinating. So the first question that's come in, Dr. Lee, is from Andrea.
Mm-hmm.
The question is, can you comment on when the single-phase arc flash standard may be published?
Well, it's an ongoing process, and then we are basically, okay, well, right now we don't have a timeline, but because that is for this 3-phase, it takes a long time. So try to get a single phase, try to regroup. Then basically that there's a lot of discussion. Okay, are we going to go through the single phase or going to the DC? And so this is the basically, again, that it I'm we have the experience that, but it's basically the time and the resource to do the work, because during the three-phase test in one lab, during the test, there inside the lab, the wall shift. So because of the pressure, so some lab refused to run the test.
Don't blame them.
Yeah, because when you look at the circuit breaker test, you have a two level. Is that right? You have a current and the voltage. It's a separate source. But for an arc flash, it's a high power. It basically combines the voltage and current. That a lot of force.
So just on an average, the intensity of the melted copper spray, is there some cutoff point when at the lower energy it's not that prevalent?
Well, that basically, okay, well, the copper by itself, you are going to see it's a function of arc duration. And of course, it's also a function of the arcing current. So it's a combine. And yeah, because if you put it in line, then erode the copper will increase the gap, and eventually arc is going to extinguish.
Right.
But the configuration we use in the arc flash test is the parallel configuration, so the gap doesn't change. If you let it go, it will continue.
I understand. Here's a question from Habib. He's saying, do we have DC arc flash standards now, currently? Nowadays, too much battery management systems. He's having issues with his battery.
This is the important one. And I think that basically, okay, well, when we try to look at it here, it's an interesting one, because we like, actually, I personally really like to have a DC model, but again, it's basically we try to look at the resource, and currently we have basic NFPA 70 has two models. Or one model. It's basically Dandong model, the maximum power. And a lot of people think this is it's too conservative. And then Everman and the PK Sen also put out the model, okay? And for that one, it's basically they derive it from a lot of reference. And then the third model, actually, we also publish a third model. It's basically use ANSYS, okay? It's a thermodynamic flow, and then try to do again, it's a theoretical one, okay? So that requires some validation process.
All right.
I think that I think the one of your competitors tried to implement our model into their software, but again, this is the basically, okay, well, I want the gentleman, I say, okay, well, this is the more like a theoretical one, and it's not validated yet, and I would like to validate the result, so I can basically feel comfortable, say, okay, well, this is the basically a reasonable one.
Right. So the next question is about the 2-second rule. How can you just explain the resolution and sustainability of arcs versus the 2-second rule?
Okay, the 2-second rule is basically it's human response. Okay, and if you are in the open area, if you are in the confined area, then 2-second rule doesn't apply. If you are in open area, normally you will be able to break away from the arc in 2 seconds. Okay, and we always think where the 2-second rule came from, and I did some study. It was published. Actually, it is from the DOT, Department of Transportation, and they tried to design the traffic light. So, according to their study, human response is about 2 seconds. So I suspect, even there's no direct evidence, I suspect that 2-second rule we use came from there.
And
it's a traffic light response, and or the basically when they designed it, okay, well, what is the response time of the human? And that 2-second rule. I remember when I did the traffic light design, the first car is the 3.8 second, and then it continued dropping. The basically, okay, the one in the queue eventually go down to about 2.2 seconds. So that I suspect that the 2-second rule come from there.
And can you comment on whether or not the advisability of applying the 2-second rule at other than low voltage?
Well, that the basically, okay, the 2-second rule, it's the base arc duration. You should look at the equipment operation. Okay, your fuse. If your fuse is higher than 2 seconds to blow the fuse, then you apply the 2-second rule. If the fuse, you blow the fuse less than 2 seconds, then you don't want to apply the 2-second rule, because that is the basically defined. The 2-second rule is defined arc duration. So if your protected device can cut out the arc less than 2 seconds, then why you apply 2-second rule?
Got it. So this question, I'm not sure. He's saying, can you please share the complete reference for DC arc flash models that you're referring to?
Yeah, the 70E has one. Okay, that's a Dendong model, maximum power.
Right.
It's basically, you look at it, what is the maximum power transfer model? And this is the voltage drop down to 50%, is that right? So that's basically equal impedance. And then the other one is the Everman model. Okay, so you can, I think you can, that paper was published. So you can find from the IEEE Explore, and then for our paper that also published in the IEEE Transaction of Industry Application. And so it's also that if you are basically, you can download it, and if you are IS member, you can download it free.
Got it. The next question says,
and the other one is, okay, some information that basically, that I think that you will be able to obtain it over there. If you can, just let me know.
do you know, are you aware of anyone doing testing or modeling above 15,000 volts?
That was basically, okay, well, this is a $1 million question. That I know that a lot of utility, they try to actually during the model development, and April also suggests that we extend the model, because we understand from the circuit point of view that the 15 kV and the 35 kV, it's basically has a very relatively similar phenomena. However, at that time, we did not run the test, and also the PAR only specify up to 15 kV, so we didn't go for that. And this is this is an opportunity for you guys, because the 1584 2018 was published in 2018. So in 10 years, we have to revise the standard. Is that right? Otherwise, it will become inactive. So yeah, there are several discussions over there. Are we going to extend it to 35 kV, or are we going to look for the one thing we didn't include it is the electrode to the back panel. So which one is more important? And that is the opportunity that we can, for the next revision, that we think that the higher voltage is more important. Then that can be the working group task over there.
Good. So here's a question. In the HCB testing that you showed, you indicated the breaker had recessed horizontal terminals. And he's saying it's hard to imagine that would be an actual fault location for an arc.
It's basically, well, when you look at it, sometimes you have a conductor come out from the wall. Is that right?
Mm-hmm.
So that is the horizontal. And then the other one is sometimes your electrode, you bend it in the different way. So it depends on the fault. If you bend it in 90-degree angle, okay, come out with horizontal, bend it with 90-degree downward. If they happen in the downward portion, that is the vertical fault. If the arc happen in the horizontal conductor part, then that will become a horizontal fault. So it really depends on where the arc is initiated.
Fair enough. I'm not sure that I understand the question. Does differential bus bar protection help in reducing incident energy?
Okay. High impedance. Okay. Actually, high impedance grounded does help. Okay, in the real life, because a lot of time the arc happen in the single phase.
Right.
So then if you have a high impedance grounding system, then we run the test. It's if you put I believe we put a 100 ohms and the 22.7 kV system, then it basically, arc doesn't start. However, if you have a three-phase short circuit, then it doesn't matter if you have the high impedance or not. The arc happen. Okay, so yeah, this is the argument in the 2002 model, because in the 2002 model, the people feel that basically, well, a lot of people prefer the high impedance grounded. And then they say, well, in the high impedance grounding, that the arc instant energy is higher. If you look at the formula over there, and so I run the test and look at the current trace for the solid ground system. You are going to have because at the beginning, especially the lower voltage, you always start with unbalanced fault. When you have an unbalanced fault, then you're going to have return current through the neutral conductor. So in other words, you have less current involved in the arc, then you have less energy released. So your instant energy will be lower, which is correct on their observation in the 2002 model. However, after one cycle, then it evolved into the three-phase fault. Then that it doesn't matter. So that's the reason why in the 2018 we took out that distinct. That basically, okay, which we didn't try to differentiate is high impedance grounding or a solid grounding because we consider this is a three-phase fault.
Dr. Lee, we appreciate your time. We've kind of reached our limit and very much value how much wisdom you've shared with us.
You're welcome.
Hopefully we'll be able to set you up for a presentation in the near distant future.
Okay.
Thank you very much for attending.
That basically, yeah, I'll be more than happy to share that or discuss with all the experts in the field.
All right. Thank you, everyone. Join us in a future date.
Okay, thank you.
So long.